So good morning, good afternoon, good evening, guys, based on the time zones you all are coming from. So guys, before we start with the session, can you all please give me a quick confirmation if you all can see my screen and hear me loud and clear as well? Perfect. Thank you for the confirmation, everyone. So before we get started, let me quickly introduce myself to you all first. So my name is Neeraj Kheria, and I've been working in this IT industry for more than 13 years now. So the main agenda for joining this entire session is to discuss all the mathematics for machine learning. So when we talk about machine learning, again, ML is basically data intensive, and before we can get started working in the machine learning component, we have to know how the data has to be manipulated. And for data manipulation, we have to know the mathematics, because again, at the end, we have to apply the logics. And for that, we have to know, okay, what exactly the logic is and how to work around it. So the main agenda is we are going to discuss on mathematics in machine learning, why exactly we need to learn it, and the topics of linear algebra, multivariate calculus, the probability, and the statistics required for becoming an expert in machine learning modules. So first of all, let's discuss on why exactly mathematics is required in machine learning. So aspiring ML enthusiasts always ask, why learn maths? Computers are faster than us at calculations, so what's the use? So it isn't the calculations, it's all about how the math needs to be performed. And ML algorithms cannot infer knowledge until we tell it how to learn. A simple example, when we are training any kid, for example, now when the kid is going to appear for the examination, the kid has to know, okay, how to add two numbers. What exactly is 2 plus 2, right? How to add how to add two given numbers, how to perform the entire arithmetic calculation on these two numbers, then only the kid can solve the problems, correct? Even like even we have to understand, okay, how to walk, how to talk, how to sing, how to do any task. We have to have the training for that particular task, then only we can apply our own logic and get the task done, correct? Same way, systems, that means each and every bot, the systems needs to understand how exactly to complete a given task, then only they will be able to perform the task correctly, right? And that exactly is why we have to make sure that we are training the entire system with the correct logic in terms of mathematics. So in terms of the entire distribution, then the biggest component is taken by statistics and probability, because at the end in ML, we work on improvising the accuracy of the prediction. And that is what we do by using the statistical components, as in how to find the mean, median, average, the percentile, the box plots. And then we have 15% of weightage given to the algorithms. Then we have linear algebra has 35% of weightage, then followed by multivariate calculus. So these all skill sets are required in terms of mathematics that we need to master before we can be proficient working with ML modules. All right. And then in terms of the entire distribution for the mathematics here, as you've seen how exactly the entire weight is defined. So let's get started on learning on the components of linear algebra. Now, if you're talking about linear algebra, again, basically here we have seen how exactly linear algebra is the most important component for any ML solutions, right? So basically, it's a part of mathematics which is used the most in machine learning. It helps in optimization, and it helps in performing the entire operations of the data. So basically, we can now it helps in optimizing data operations that can be performed on pixels such as sharing, rotation, and much more. And we can understand why linear algebra is such an important aspect when it comes to mathematics for machine learning. So let's say we start off with the mathematics for machine learning now and understand as much as we can. So now, before we start, remember there is no one that can master anything in the world. Obviously, even the expert data scientists, even the expert ML engineers, they have some gaps, right? So basically, that's why it takes time, patience, and the real world experiences to help us master the mathematics that we need to learn. But this entire session is going to make sure that we are going to have an understanding, and that with the right approach. All right, so let's get started. So first of all, we have scalars. So now what exactly we understand by scalars? So to put it in simple layman terms, scalars are just values that represent something. It can be something like the size of a house to temperature in an engine, or scalars can help us represent them and their values. So the mathematics in scalars, just a simple arithmetic value itself, right? So for example, let's say now if we talk about an example here, then suppose a laptop costs around 50,000, right? That 50,000 INR, it is on a sale for 50%. That means it is half the price, and then we can calculate the price by dividing by 2, as is 25,000, correct? So if you want to buy 5 of the same laptops which are on sale, we just have to multiply this number, that is the sale amount, by 5, and then we'll be having the entire value in terms of the scalar value, right? Suppose let's say if you don't want to buy the accessory, then we have to remove that from the value itself. That means we have to remove the accessory value if you don't want that, correct? So in simple layman terms, again, it's a scalar value, simple arithmetic and nothing complicated. And that exactly is what we need to know about scalars. So let's now, as we discussed on scalar, let's move to our next topic that we have as vectors. So vectors are a bit complicated. So basically they are different for different backgrounds. So computer science people can interpret vectors as a list of numbers that can represent something. Physicists can consider vectors to be a scalar value with a direction, and it is independent of the plane. The mathematicians can take vectors to be a combination of both, and they can try to generate two, or we can say simply generalize it for everyone. That's how this can be structured. Now in machine, and again, all of these standpoints are absolutely correct, and that's what makes it so confusing for everyone learning about linear algebra for mathematics for machine learning. That exactly is what makes it a bit complicated. So now let's move on to our next module. So basically, okay, if you talk about in the same concept in detail, then in machine learning, basically we usually consider vectors in the standpoint of a computer scientist. When the data is tabular consisting of rows and columns, data is again, and when a data is in the format of pixels, as in pictures, we consider them as vectors, because again there we define the entire vectors in the entire picture as well in multiple rows and column pixels, right? So that is also considered as a vector. That's our basically bound to the origin and transform them to the matrices and perform operations that we are going to talk about at later point of time. Now, since we have a brief idea about vectors, so let's jump over to the operations that we need to know when to work with the vectors. So before we discuss further, let's discuss on the vector operations as well. So operations on vectors can be applied only when we know what kind of data we are working with. Suppose we have a pixel data and we want to apply rotations, but end up doing something wholly different, then a model will not work because it is doing the wrong operations here. So to make sure that we know what exactly we are working with, we have to apply the required operations, correct? And then we have vector addition as in a dot product. So basically this operation is the addition of two different vectors, but it is not just a simple arithmetic value. It is actually the displacement that we achieve from the working of both of these vectors. The below diagram will help you understand better. As you can see, we have two different vectors here. So basically it is the displacement that we achieve from working with both of these vectors that we consider as a part of vector addition, as a part of dot product. All right. So as you can see here, we have two vectors, v1 and v2, right? We have v1 and we have v2, and to add them and the effect together, for example, if v1 has values 1 and 2, if v1 has a value of 1 and 2, and v2 has value as 1 and -1 for the x and y axis respectively, the effective v1 plus v2 will have the value as 2, 1, which is to add the scalar values of these different vectors. And that's why this is called as a dot product. Now after this we have scalar multiplication. So when a vector is multiplied with a scalar, it either grows or shrinks, and positive and negative scalars either grow or shrink in the vector. So if a vector is multiplied with a constant, it either grows or shrinks accordingly, as we discussed. And this can be used in something called as a shearing. This can be used in something called as a shearing. So we have something called as a shearing, which can be used as a part of scalar multiplication. So sharing helps in the manipulation of the pixel information. So the equation for scalar multiplication is obviously k to power a, or k to power a is equal to power a. And this diagram is basically used for understanding how exactly this is going to work. So basically here we have the entire, again, with this, as you can see, let's move on to the projection itself as a part of the kv1. And again, here we have the entire value for minus kv1. And then we have the entire scalar projection that we are going to work on. So basically, when we're talking about the projection of a vector on other, then the projection of a vector on to other is what we are calculating here, is what exactly we are calculating here. So projections help us to find the shadows of a pixel, and they can be used to find the length, distance, and map a 2D object to a 3D object for better analysis. And with projections done, we have finished the basics of what is needed from the pure vectors. Now let's move on to our next topic, where we are going to discuss on the matrices as a part of mathematics for machine learning itself. So now if we talk about the matrices, now matrix is basically a composition of numbers that you all have learned back in our school days. So matrix is basically a composition of numbers, symbols, or expressions in a rectangular array. And we use matrices to convert expressions of the vector forms to array. And they make operations easier, as this is what we work with on computers. So that exactly is what we can define as a part of the entire equation matrices here. Suppose let's say we have two equations. We have 2x and 2y is equal to 10, and then we have the second equation as 4x plus y is equal to 18. This is our first equation, and right here this is our second equation. So basically, if we multiply, now how exactly we are plotting this here? So basically, if we multiply here both with, if we multiply equation 1 with 1, right? Suppose here we will multiply this with 2, and then we multiply this with minus 1. We multiply the above equation with 2, and we will multiply the below one with minus 1. Then by simplification, we are going to get 4x plus 4y is equal to 20, and here we are going to get minus 4x minus y is equal to minus 18. And then if we add this sum here, then at the end we are going to get 3y is equal to 2, where we are going to get the value for y is equal to 2 by 3, right? Where we can say that x is equal to 13 by 3 itself, and that exactly is what we can plot here as a part of matrix. Now, when we are plotting this as a part of matrix, it becomes easier to solve the problem. And when we use matrix operations to solve the problem efficiently, then that simply improvises the speed with which we can carry out the operations. Now, these are something that we can use to represent in our computers. So functions represent data in a generalized form, and that is the reason why they are so essential to understand as a part of machine learning concepts. And these functions can be solved to obtain the coordinates where we can use them, and then we can use them for something else depending upon the application. All right, so now let's move further. So here we have matrix operations. So basically they are multiple now. Even in matrix, there are multiple types. We have row matrix, column matrix, square matrix, diagonal matrix, identity matrix, and then we have sparse matrix, and then we have dense matrix. So basically, in terms of the matrix operations, there are multiple operations available. First of all, we have addition. So matrix addition is a simple process of adding the corresponding elements of two different matrices. For example, we have matrix as 2, 2, 4, 1 plus 2, 3, 1, 4. And now we will have to add these two matrices together. So again, we can add this as simple as C is equal to A plus B, where A and B are these two individual matrices that we have to add as a part of the component. So here we have added these two values as 2 plus 2 is equal to 4, 4 plus 1 is equal to 5, 2 plus 3 is equal to 5, and 1 plus 1 is equal to 5. So simply adding the corresponding elements of the matrices, that is allowing us to add to make sure we are having a matrix addition done. So here we are adding 2 plus 2 is equal to 4, 2 plus 3 is equal to 5, 4 plus 1 is equal to 5, and then 1 plus 4 is equal to 5. A simple addition in terms of matrices that we can perform here. Same way when we are now, same way here we can also work with the matrix subtraction. So here we can subtract the corresponding elements in this operation. So 2 minus 2 is equal to 0, 2 minus 3 is equal to -1, 4 minus 1, 3, and 1 minus 4, -3 as a part of simple matrix subtraction. And when we are working with matrix multiplication, so multiplying the rows of matrix 1 with the column of, and need the rows of matrix 1 need to be equal to column of matrix 2 for it to work. And here we can have formula for 2 by 2 matrix. And the formula for 2 by 2 matrices, we have to first of all multiply A1 by B1. Then we have to multiply A1, here we have to multiply the A12 by B21, and then A11 by A12, and so on, so that we can get the entire matrices available. For example, we have these two matrices that needs to be multiplied together. We have 2 by 2, 4, 1, and 3, 2, 3, 1, 4. So in order to multiply them together, first of all, we have to multiply them by one row with each and every column. For example, here we multiply 2 by 2 plus 2 plus 2 by 1. Then here it has to multiply by 2 by 3 plus 2 by 4. That means the first entry has to be multiplied by, now here we have to multiply the first column, first row by 2 by the entire column altogether. So here it has to go as 2 by 2, then plus, then it has to be added to 2 multiplied by 1. And again for the second one, it has to be 2 multiplied by 3 plus 2 multiplied by 4 as a value. Same way for 4, it has to be 4 multiplied by 2 plus 4 multiplied by 1 plus 1 multiplied by 1 altogether, right? And then it has to be 4 multiplied by 3, and it has to be 1 multiplied by 4. That means each and every row has to be multiplied by each and every column altogether. And then we can simply add this sum together, and that's how the entire matrices are going to be multiplied. Now we have the transpose of a matrix. So transpose is basically interchanging rows and column of a matrix. For example, here we have 2, 2, 4, 1, right? So the row becomes a column and the column becomes a row itself. That's how exactly it works. So we have row has been transferred to the column as 2 by 2, and then the second row has been transferred to the other column itself as a 4 by 4 matrix. And that is usually represented by a simple T, which usually flips the entire row and column as we define. So after transports, now here we have seen how we can make use of the transpose. Now we have the determinant of a matrix. So basically it is a scalar value of a matrix, and it gives us a product of eigenvalues of the matrix. As a small overview, so basically the determination of matrix is a value of a matrix, especially if it tells you that the scalar of a matrix. So basically the determinant gives us the product eigenvalues of in the matrix, and the determinant can be found by the following operations. So like we have the matrix here as A, B, C, D, E, F, G, H, I. And then now here for finding the determinant, here we are going to add to simply multiply the first column here as A multiplied by EF and HI, the second row, second column, as you can see here, and then we are going to subtract that by, and here we define then B multiplied by the DE, the DF, and the GI, and then C multiplied by AB. Sorry, we have going to multiply this by DE and GH. Basically to find the entire determinant here. So basically in terms of the determinant, here we got the result as AEI plus BFG plus CDH minus AFH, then minus BDI minus CGE. So as a part of the determinant that we can define here. And then we have inverse of a matrix. So when the matrix is multiplied with inverse, it gives us an identity matrix, and inverse helps us in applying transformations efficiently. So some matrices do not have an inverse, which means that the information they hold is not reliable, or they are very noisy. So, and in some cases, matrices do not have an inverse, which means that it is not possible to determine the value of the matrix, as the value of the matrix does not have sufficient data to help us finding the inverse value. That's why we cannot find the inverse for every matrix that we have. So for 2 by 2 again, and for inverse, we can find by 1 by AD minus BC. as we define the entire value for inverse. Same way for 3 orders and above, like we have A, B, C, D, F, D, F, and G, H, I. So here we are going to find the value for EF and HI, like we have seen for eliminant. Same way for DF and for HI, and so on. Now, next we have the vectors as metrics. So vectors can be easily translated to a matrix. It can be easily translated to the matrix, and vectors can have either 2 or 3 components along with the same angle from the origin. So this can be easily translated to any matrix. It can be used to perform 3 of the most well-known applications that we have when it comes to pixel data. So we can perform scaling, we can perform rotation and shearing on the pixel data. We can make an algorithm that can learn the factors of the pixels and perform better when it comes to getting the output. For example, let's say vector v1 is going to be 3x plus 4y, and vector v2 can be x plus 2y, right? So how do we transform them into matrices? It would have we already have to use the concept that we had discussed in the matrix introduction part, right? So basically these can be converted easily as 3 or 4. The vector first one can be converted as 3 and 4 as the value for x and y, and same way here we can have 1 and 2 as the matrix converted for v2 is equal to x plus 2y, correct? As a simple transformation that we can have for these two different matrices. And some well-known operations are, again, we can assume that our operations are on 2 variables only, meaning that it is a 2 by 2 matrix. So the scaling matrix scales the vectors and makes it big or small. And the shearing will change the vector by a particular side or coordinate. And the rotation is rotating the vector around the origin according to the values provided. So these are really simple to implement when we have a vector in the matrix form. Hence the convergence of these two kinds. So now that we are okay with vectors and matrices, let's look at the two most important ways to solve equations, which are the row echelon method, and then we have inverse method. So let's discuss on that. So in terms of the vector as matrix, first of all, matrices can help us solve equations and obtain solutions. And as we discussed, there are two ways. We have row echelon method and then we have inverse method. So row echelon method is basically, let's say, if we take some vectors in the linear equation form. In the linear equation form, like we had 2x plus y minus z is equal to 2. We have x plus 3y plus 2z is equal to 1. And then we have x plus y plus z is equal to 2. So now let's take them into a matrix form where we can obtain 2, 1, minus 1, 2, and then we have 1, 3, 2, 1, 1, 3, 2, 1, and then we have 1, 1, 1, 1 as a part of the entire matrix cell that we can define here. So step 1 is again, here we are going to make sure that we have now a finished, we should be having a finished matrix into its entire Euclidean format. So basically the main use of using this entire Euclidean format is we may have not noticed that if we, or we may have that we have solved the equation itself. So yes, for our equation has been solved and we have the values of x, y, and z defined. So basically here we can make use of this entire Euclidean method to solve and find the values of the vectors. And there is another way to do the same thing by finding the inverse. So let's go on for that now in an article for mathematics and machine learning. So now we are going to discuss more about the inverse method. So suppose we have some equations as 4x plus 3y minus 13, and then we have minus 10x minus 2y is equal to 5. Then we convert that into matrix form, is going to be like this one, minus 4, 3, and then minus 2y, minus 10, 2 is equal to 2, 13 minus 13 by 5. So we know that again a dot b is equal to c. Thus, if we multiply both sides with the inverse of a, it shouldn't change the values of the equation, right? So there we are going to get the inverse of a. When you multiply them both by inverse of a, then we are going to value of the equations as a minus 1, and then we are going to get the a dot b and a minus 1 dot c. So now if we assume that b is the matrix whose value we can find, so it becomes easier for us to do that. So we can find the values of a and a minus 1, and then we can cancel out each other and give the value and give us an identity matrix. We are then left with b is equal to a minus 1 as the inverse value of a multiplied by c itself. So from this method, we are able to find the values of our x and y very easily. And these methods come in really handy when we want to solve the coordinates for the vectors and much more. So this is basically the overview of what exactly we need to learn as a part of the machine learning. And we can definitely go in depth with these concepts. But again, for now, like having a basic understanding of these is going to be enough. And then we are going to explore these things in detail once we start working on these elements one by one. So by now, we do have an understanding of what exactly vectors and matrices are with the entire operation so that we can resume further in our study. All right, so now let's discuss on the entire vector as matrix. Now, and we have other components that we are going to discuss as a part of Eigen vectors. Now we have already discussed vectors as matrix, how we can make use of the entire component of vectors, how we can define the entire vector components. Now we have the entire concept for eigenvectors. So basically eigenvectors and eigenvalues. Let's suppose we have a rectangle in which we have two vectors, v1 and v2. Now, what if we apply the sharing operations on this rectangle? So we can see that vectors v1 and v2 scale in the size, but there's something much more than what meets the eye here. So the vector v1 has also moved its direction, but that is not the case with the vector v2. So even though the scaling of v2 has changed, the direction has not. The direction remains same. So no matter we apply scaling or sharing operations, the direction of vector v2 shall not change, and that is what makes v2 an eigenvector. So basically that's an eigenvalue. It's basically a list of factors by which the vector transformations do not affect the direction of an eigenvector. And putting it into a definition, eigenvectors are those vectors that do not charge, or we can say that do not change its direction even if transformation is applied to them. And the list of values by which the transformations are applied on the eigenvector, and we have to make sure that the directions does not change in its eigenvalues. So basically, this helps us in having a quick understanding on what exactly eigenvector is. But what is the main significance of using eigenvector? So what exactly real purpose they do serve? So basically, there are multiple applications of the linear algebra in terms of machine learning that we are going to discuss. So first of all, the first use case is principal component analysis that we refer as PCA. And it is one of the most important techniques that utilize the linear algebra in depth. So the main motive behind PCA is to reduce the dimensionality of the data using ion decomposition and matrices. And as we are going to discuss further on the entire PCA component, then we'll be able to see how exactly it is structured, right? Then when we are working with the images, now when we are working with the images, we can use the concepts of linear algebra to scale, smoothen, crop, and much more. We have predefined operations that we can use to create operations that can take care of all the components that we have discussed so far. So when we are working with encoding of data sets, so this is another application where linear algebra is used. And we have inbuilt functions in many languages that help us in encoding the strings to characters or something else. And these functions are made using the linear algebra. Now, we may know about optimizing the outputs that we can get the most optimum values needed by a model. And there is mostly the use case of multivariate calculus, but there are certain times when we use even linear algebra equations and more than can be used to optimize a model and the weights that yields the outputs. And a singular value decomposition, or we refer as SVD, it is basically another application which is of the same kind of PCA, but they are used for single dimensions. And this helps in the reduction of the noise. It helps in improving the quality of the information that is obtained from the dimensions and so on. And it uses the eigenvectors and matrix factorization for the entire work process. Then we have the latent semantic analysis for natural language processing. So basically images are now here the here we can make use of the sparse matrices factorization with the SVD to give us the most important parts of the text document. This can be used for the NLP part. And then we can use deep learning. So where deep learning is also going to use the linear algebra because it works on optimization and more to give the best possible output by using the components. So that's why these all components are an integral component for machine learning models. And then we have multivariate calculus. So multivariate calculus helps in solving the problems of optimizing the machine learning model. So it is one of the most important parts of mathematics for machine learning. It helps us in solving the second most important problem that we face in developing machine learning models. The first problem obviously being the pre-processing of data, and the next one being the optimization of the model. And this helps us in optimizing and increasing the performance of a model and give us some of the most reliable results. So how does something that almost half of the class hated help to solve such a problem? Let's break the entire component for multivariate into smaller components. So now here we make use of differentiation. We make use of the entire components for the power rule, the sum rule, and the product rule, and the chain rule. So these all components are going to be defined here along with the partial differentiation, which is going to be part of this multivariate calculus. So again, thank you so much for being a part of this session, guys, and have a great day ahead. Take care. Bye-bye.